Hello, this is a question on sequence and series. We have two questions. The first one, we are asked to evaluate the sum from 1 to infinity of 3 into 1 quarter to the power r. First question, evaluate this sum. R starts from 1 to infinity of 3 into 1 quarter to the power r. Okay, so we are actually looking for the sum to infinity of this series. So how do we go about that? We must first of all check to see what type of series this is. The only way to do is to get the first three terms of this series, and then we check if we got, for example, a common ratio or a common difference. So we can work it out. Now, general term of this series is usually what has been summed. All right. So we have TR is 3 into 1 quarter to the power r. This is the general term for this series. So the first term will be when r is 1. When r is 1, we have 3 into 1 quarter to the power 1. That gives us 3 into 1 quarter, which is 3 quarter. The second term is when r is 2. 3 into 1 quarter squared. This is the same as 3 into 1 squared is 1, 4 squared is 16. That gives us 3 all over 16. The third term is when r is 3. And so we have here 3 into 1 cube is 1, 4 cube is 64. That gives us 3 all over 64. And so this series can be written in the manner 3 quarter plus 3 all over 16 plus 3 all over 64 plus and so on. So this series is the same as this. We are summing to infinity. All right, looking at it carefully, we see that it can only be a geometric progression. It can't be an arithmetic progression. All right, if we take T2, T3 minus T2, for example, this is T3, 3 all over 64 minus 3 all over 16, we don't get the same result. Okay, this is simply what? The LCM is 64. All right, so we have 3 minus 4 times 3 there is 12 because 64 divided by 16 is 3. 3 times 3 is 9, sorry. All right, it's 4. Oh my God. 64 divided by 16 is 4. 4 times 3 is 12. So here we have negative 9 all over 64. If we take T2 minus T1, so we're just checking. We're checking if it's an AP. T2 minus T1, well, 3 all over 16 minus 3 quarter. So LCM is 16. So we have 3 minus 16 divided by 4 is 4. 4 times 3 is 12. This gives us negative 9 all over 16. Negative 9 all over 64 is not the same as negative 9 all over 16. So it isn't an arithmetic progression, not an AP. Now, if we check the other way around, T3 divided by T2, all right, to check if it's a GP, T3 divided by T2, this is our T3, 3 all over 64 divided by 3 all over 16. All right, we maintain the first fraction, 3 all over 64. Change this to multiplication, invert this. Okay, so now we have 3 here cancels, 16 here 1, 16 here 4. That gives us 1 quarter. If we take T2 divided by T1, all right, T2, this is T2, 3 all over 16 divided by T1. T1 is 3 quarter. All right, again, we maintain the first fraction, 3 all over 16. Change this to multiplication, invert this, 4 all over 3. So see 3 cancels, 4 here, 1, 4 here, 4. So again, we have 1 quarter. So we see we have the same result. It therefore means that there is what we call a common ratio. And any series that has a common ratio is a geometric progression. Okay, so it is a geometric progression. Now, summing to infinity of a geometric progression is usually written as S infinity, and it has a formula. It is T1 all over 1 minus the common ratio. All right, so that sum now becomes our T1 is 3 quarter, So we have 3/4 divided by 1 minus our common ratio. All right, let's do that aside. 1 minus our common ratio. This is a fraction, so we can just make this one a fraction. 2 LCM 4. 4 divided by 1 is 4, multiplied to 1 is 4. 4 divided by 4 is 1, multiplied to 1 is 1. So we have 3/4. So finally we have, let us take it up there. All right, so we have 3/4 divided by 3/4. 3/4 divided by itself, so our answer is 1. So this series sums up to 1. Right? So the sum of this series is 1. That does it for the first question. Please, if there are any worries or issues, we would like to read them in the comment section. Now let's take the second question. Let's take the second question. If the sum of the first n terms of a series is given by, sum of the first n term is given by 2n squared plus n. All right? So A, find an expression for the nth term of the series. How do we get the expression for the nth term? The nth term always have a relation with the sum of the first n term. That relation is always given as Sn minus Sn minus 1. It's always like that. All right? This is the nth term of the series. So we know Sn is given up there. So 2n squared plus n minus, now what is Sn minus 1? This subscript n minus 1 will now take the place of n in that expression. So now we'll have Sn minus 1 is equal to 2 into n minus 1. So everywhere we find n, we replace with n minus 1 squared plus n minus 1. So this gives us 2n squared plus n minus, let's first of all evaluate that. N minus 1 squared is n squared minus 2n plus 1 plus n minus 1. All right, let's open that bracket. So it becomes 2 multiplied to n squared, 2n squared, 2 multiplied to negative 2n, negative 4n, 2 multiplied to 1 plus 2, and then plus n minus 1. All right, so we are having 2n squared plus n minus all of that. So let's open that bracket with respect to this minus sign. 2n squared plus n, negative times positive 2n squared becomes negative 2n squared. This negative times negative, positive 4n. This negative times positive, negative 2. This negative times positive, negative n. This negative times negative, positive 1. So finally, well, we have to simplify or reduce this long expression. We have 2n squared minus 2n squared gives us 0. All right, so we have finally we have n, this one, plus 4n minus 2 minus n plus 1. All right, so we have n minus n 0, so we're left with 4n. Negative 2 plus 1 gives us negative 1. And so the expression of the general term or any term for this series will be Tn given by 4n minus 1. This is the expression for any term in that series. That answers the first part of our second question. Second part, we are asked to show that the series is an arithmetic progression. We are not verifying, we are asked to show. That means it is an arithmetic progression. We must show that it is an arithmetic progression. All right. Again, our Tn is in this box. That's what we have. To be able to demonstrate that, we need at least the first 3 terms of that series. Now, the first term is when n is 1. So we're going to replace n with 1. That gives us 4 minus 1, which is 3. So our first term in that series is 3. Second term is when n is 2. And so we have 8 minus 1, we got 7. Our third term is when n is 3. And so we have 12 minus 1, which is 11. So from here, our series can be written as 3 plus 7 plus 11, and so on. This is our series. We have the first three terms. Now, is it a GP? Let's start by checking whether it's a GP. With the GP, there is a common ratio, which is the value gotten from T3 all over T2. And this value must be the same as T2 divided by T1. All right, if we have this equality valid, then we'll say it's a GP. Now let's do that. All right, so we have, if we have to do that, let's draw a line here and do it here. Now T3 divided by T2, this is our T3, 11. 11 all over T2, T2 is 7. Is it the same as T2 divided by T1? 7 all over 3. Is 11 all over 7 the same as 7 all over 3? That is not true. Therefore, not a GP. Alright? This was just in case someone was doubting, because the question already told us that it's an AP. So there's no place for this. This was just for someone who might be doubting. Alright? Now, let us now show that it is an arithmetic progression. Alright? Let us show that it is an arithmetic progression, because it is an arithmetic progression. Again, our Tn is 4n minus 1. Okay. We have our T1 was calculated already. It's 3, T2, 7, T3, 11. Now, for an arithmetic progression, T3 minus T2 must give us the same result as T2 minus T1. If we don't have this equality, if we don't have these results being equal, then it is not an arithmetic progression. Our T3 is 11 minus T2, 7. Do we have the same result when we take 7 minus 3? 11 minus 7 is 4, and 7 minus 3 is 4. So we see there is equality. Hence, the series is an arithmetic progression as required.